So I think we already did this one. So let me just quickly redo this one. The Cr has an oxidation state of zero. Cl over here I think is +7. CrO2 -1, that's +3, right? ClO3 -1, that's +5, right? So Cr is going from what? It's going from 0 to +3. Cl is going from it's going from +7 to +5, so it gains 2 electrons, while Cr is the one that what does it do? Loses 3 electrons, right? So I'm going to multiply Cr by 2. So there's going to be 2 Crs, and I'm going to multiply the Cls by 3.
I don't understand why you multiplied by 2.
Which one?
Because you multiplied by 2. Yeah.
The electrons gain and loss, they have to be made equal, right? I mean,
Okay.
So and you can then basically just balance the hydrogens and oxygens, right? So you got how many? 12 plus 1, 13. That's 8 plus 9. How many oxygens do you have? Sorry, 4 plus 9, that's 13, right? So I guess I said the only thing wait a second, how many oxygens do you have? I think just a 2 over here would balance it, right? Just count. Yeah. That's 12 plus 2, that's 14. 4 plus 9, that's what? 13. And 2 and 1, sorry, that's 14, right? And 2 hydrogens, 2 hydrogens, so it's balanced, right? So you got this, right? You clear it? Is this clear?
Yeah, it's clear.
Achha, so I don't there was a thing called disproportionation, where what happens when the same element gets oxidized and reduced at the same time. So you got this equation. You got chlorine turning into Cl -1, also turning into Cl +5. So getting reduced, gains 1 electron, getting oxidized, loses 5 electrons. So which is why I multiplied the first one by 5, the second one by 1. So I would have 5 Cls, which are -1. And I will have, and on the other hand, I'm sorry, I'll multiply this with 1. So I just need 1 Cl, which is +5. Okay? Is this clear how this equation got balanced?
Yeah, it's clear.
Anyways, now, so we're going to start with, so we are going to start with A2 electrochemistry. Now the whole idea about electrochemistry in A2 is that you've got reactions where some elements are gaining electrons, some are losing electrons. Previously, the equation was already made for you, but now what you have to do is you have to learn how to make an equation from scratch. So for example, if I tell you, if I give you PbO2, now you've got no idea whether it likes to lose electrons or it likes to gain electrons, right? So what does PbO2 want to do? We personally have no idea what it wants to do, right? We don't even know, like, if it likes to lose electrons, then how strongly does it like to lose electrons? We don't have both informations. If I give you, there are very few elements about which you might be sure. I mean, Sn2 plus, no idea whether it wants to gain electrons, whether it wants to lose electrons. But there's some very, very few elements where you might have some idea. So for example, if I ask you what sodium wants to do, to kya hoga, what is the answer? Does it like to lose electrons? Does it like to gain electrons?
Lose electrons.
Okay, and it likes to lose electrons vigorously, right? So it has a very strong tendency to actually lose electrons. So very few. So you have I mean you can just I mean for I mean to be you can just guess this for very few elements. What does Cl2 like to do? Lose electrons or gain?
Gain electrons. Gain electrons.
Okay, so this one likes to. And it's a very reactive substance, so it likes to gain electrons kind of strongly. So basically, we need to develop a system, and the system is going to figure out what the substance wants to do, whether it wants to lose electrons or whether it wants to gain electrons. So we're going to come up with a system that's going to figure out what it wants to do, and whether it wants to do it strongly or not very strongly. Like if I talk about gold, we know it loses electrons, but it doesn't really like to lose electrons. It has an extremely low tendency to form ions. So it's probably never going to form ions. But it never actually forms negative ions. So that means we know that it doesn't really like to gain electrons, but never really forms positive ions. So it's kind of inert. So the system that we're going to build that is going to determine what it wants to do is known as, I mean, you figure this out using standard electrodes. And what standard electrodes do is they help you measure standard electrode potentials. So we're gonna discuss this. So we're gonna discuss this system. So for example, if I know that sodium likes to lose electrons, what I would do with sodium is I'm gonna take a beaker, and inside that beaker, I'm going to place a metallic bar that's made out of let me just 1 second. So forget it. So I'm going to place a metallic rod that's made out of sodium. I know that sodium likes to lose electrons. This is an overly simplified diagram. It's very hard to actually handle sodium in the lab because it's very reactive and it's explosively reactive. But so just imagine it as an overly simplified diagram. I take a piece of sodium and I put it in a solution, aqueous solution of sodium ions. That could be NaCl aqueous, probably. So the solution contains sodium ions. Now, two things are possible. One is that either sodium likes to lose electrons, and when it loses electrons, it's going to form sodium ions. Or secondly, the sodium ions would like to gain electrons. And they could turn into sodium. The one or two, first one or second one. Consa, which one is more likely to happen? Which one? The first one or the second one?
Do you mean which of the two equations?
Yes. I mean, there are two possibilities, right? Either sodium would lose electrons or the sodium ions that are in the solution would gain electrons, right? So which one is more likely to happen?
The sodium will lose electrons.
To this one, and so I mean, it doesn't really like to gain electrons. Sodium likes to really strongly lose electrons. So we know that the first equation is going to happen. We know this, right? We already know this. So sodium atoms would start turning into sodium ions and they would start dissolving. So the number of sodium ions in the solution and their concentrations, they would start to increase. Because sodium has, so all the sodium atoms in the metallic rod would start losing electrons. But those electrons have nowhere to go because there's no reaction happening. So those electrons which are being lost are accumulating on the metallic. So they're all accumulating on the metallic rod because there's no other element that's gaining electrons. So that's it. Sodium loses electrons. And now metallic rod has delocalized electrons already. So it can accommodate a few more electrons. If sodium atom decides to lose an electron, a few more electrons could become part of the delocalized electron cloud. So what would happen is that the metallic rod would slowly start building up a negative charge, right? Is that clear?
Yeah, that's clear.
And your solution will slowly start developing a positive charge or a positive potential because there's more and more sodium ions getting formed, right? So there's a lot more positive ions compared to negative ions. So overall, the solution will have a positive potential building up. And so sodium will continue to lose electrons. There would be more electrons accumulating on the metallic rod as sodium atoms continue to lose electrons. And there would be more sodium ions getting formed as they continue to lose electrons. The negative charge becomes larger and larger. So the negative charge builds up. At the same time, the positive charge builds up as well in the solution. It becomes larger because you got more positive ions, right? But this will not go on endlessly. There would come a point when the negative charge, there would be so many electrons accumulating on the metallic rod. The negative charge would be so large that what will happen instead is that the sodium ions, because of the large negative charge of the metallic rod, will start getting attracted back to the electrons. So now the second reaction also starts. So basically the opposite reaction also begins. And it had to begin because the negative charge would not build up endlessly because no one is gaining those electrons. No one is taking up those electrons. So the electrons would accumulate and they would become more and more negatively charged. So eventually they would start attracting the positive ions back again. And that's when you have an equilibrium, a reversible reaction, and you set up an equilibrium gets established. Is that clear?
So there's an equilibrium because the ions are being lost and gained.
Well, yeah, now it's both, right? I mean, initially it started off with sodium losing electrons, right?
Yeah.
And so more and more electrons on the metallic rod, right? It became more and more negatively charged. But up till a certain point, at a certain point, the negative charge becomes so large that it starts to attract the positive ions back again. So now it's both forward because when sodium loses electrons, the negative charge becomes very large. That attracts the sodium ion back again. So now it's both things happening. Okay? Is this clear?
Yep, it's clear.
So moving on, this so we've got an equilibrium established. And every time an equilibrium will get established until someone either removes, because there was no one taking up, there was no reaction going on. So you ended up with an equilibrium. Okay, the right way to write this equilibrium is that it's always a reduction in the forward direction. and oxidation in the backward direction. It's the same reaction. I said, now the thing is, the metallic rod will carry a negative charge. This negative charge will become a constant. Why? Because it's now in equilibrium. So if you have 100 electrons on it, it will remain 100 electrons, although the reaction is still going on. Sodium is continuously losing electrons, but because of the larger negative charge, the ions are getting attracted back again. So the amount of electrons kind of remains exactly the same. TK, is that clear? Okay, once equilibrium gets established, the charge that has built up on the metallic rod is not going to change. Is that clear?
Yep, that's clear.
This is what's next. What you're going to do next is you just take a voltmeter and you're going to connect it. Connect it, and you're going to measure the voltage. And a certain voltage appears on it. That voltage is going to be referred to as the E naught. For sodium, this is minus 2.71 volts. So that's known as your standard electrode potential. So that's the potential that has built up on the sodium electrode. It's a very low potential. It's a very negative potential because sodium really likes to lose electrons, which is why your electrode had a lot of electrons on it, which is why it was negatively charged. That's why you're getting a very low potential. So the idea of an electrode potential is a low or negative potential indicates that sodium really likes to lose electrons. If it wanted to gain electrons, then there would be no electrons over here. But in this case, you're going to have a very, very low potential, which is going to be a negative potential. Is this clear?
Yep, it's clear.
So what is the potential telling us? It's telling us what sodium wants to do. A negative potential indicates that it wants to lose electrons. A larger negative potential or a bigger value indicates that it wants to lose electrons a lot. So tell me one thing, if I replace sodium with potassium, like if the whole electrode was made for potassium, would you have a lower potential or a slightly higher potential compared to this one? Is sodium more reactive or less reactive?
More reactive. Oh, sodium's less reactive than potassium.
Potassium is more reactive, right? So what would be the potential on potassium? Like, just guess the potential. What?
It would be larger.
Like bigger, like more negative or more negative, right?
Yeah.
So because it's going to produce a lot more electrons. So there's going to be a lot more electrons. It's going to be more negatively charged, right? So if you copy. So all these potentials are given. And copy. So all these potentials are given. So you can see sodium at the top, that's negative potential. So the more negative potential it is, the more likely it's going to lose electrons. You can have a look at aluminium likes to lose electrons. Here's aluminium. You can see it's got a minus 1.66 potential. You got barium over here. So calcium over here. Calcium's got a very low potential as well. Calcium really likes to lose electrons. Then you have other elements like what other metals that like to lose electrons. Just a second. Here's lithium. Why do you make batteries out of lithium? Because lithium really likes to strongly lose electrons. It's got one of the lowest potentials. Potassium is kind of similar. It's also very, very low. Okay, so that's about losing electrons. And remember, that's the first type of electrode that we've made. This electrode is basically when you try to figure out the potential or the tendency for a metal to lose or gain electrons. So whenever you have a metal, which is in equilibrium with so that's the first type, metal and aqua science electrode. Okay, let's move to chlorine, the second type of electrode. The electrode depends on what compounds. I mean, the concept is exactly the same. The only difference is it's going to change if the substance is either a solid or a gas or an aqueous. So this one, I'm going to call it a gas aquasign electrode. Now, in this one, I want to figure out what chlorine wants to do. So I'm going to construct an electrode again. So I want to figure out whether chlorine likes to gain electrons and it wants to form Cl ions, or the reverse, whether Cl ions, they like to lose electrons and they want to turn into the greenish yellow gas back again. Now, since I know about chlorine already, क्या होगा इन दोनों में से? Which reaction is more likely to happen?
The second one.
What does chlorine want to do? Gain electrons or lose
It
electrons?
wants, yeah, gain electrons. So it would be the first one.
The first one. It doesn't like to do the second one. If it, like, your table salt never changes into chlorine gas because Cl minus one doesn't really like to lose electrons. So now the concept is exactly the same except it involves a gas. So what's going to happen is you're going to have what's going to happen is you're going to have a gas electrode. TK, which would kind of, let's say, look like this. So think of this as a gas jar. So what I'm going to do is I'm going to have the Cl ions in solution. And I'm going to insert, I'm going to have chlorine gas coming from the other side. So there's Cl2 gas coming in, and it's obviously in gaseous state. The Cl ions would probably be coming from NaCl aqueous. And this time what I have is I've got, like, I know that Cl2 wants to gain electrons, right? But who's going to give it electrons? There's no delocalized metallic electron cloud. So where would it find those electrons? Because like if it wants to form Cl-1, where would it get those electrons? So I would have to insert a platinum electrode. The platinum, as a platinum over here, just a second, as a platinum over here is going to act as a source of electrons. I mean, like if it's got a delocalized electron cloud, so any potential that builds up, it's going to build up on the platinum electrode. Like if somebody wants to give it electrons, it will be able to give it electrons. If somebody wants to take its electrons from its electron cloud, they would be able to take its electrons. So a potential would build up on the platinum electrode, right? Is that clear? You roll samajh aaya ki what does the platinum electrode do?
Yeah, that makes sense.
So here are the chlorine molecules coming in. And these chlorine molecules will they'll try to gain electrons from the platinum electrode. So what will eventually happen to the platinum electrode? It's going to become positively it's going to become positively charged. There's going to be more and more positive charge that's going to build up on it. And because the chlorine molecules are gaining electrons and they will turn into Cl ions, which will become part of the solution. So your electrode this time is becoming more positively charged because the substance likes to gain electrons, and your solution is becoming more and more negatively charged. The chlorine molecules are going to keep on coming in, and they're going to keep on gaining electrons. So the positive charge would become larger and larger. At the same time, you're going to have more and more Cl ions. So the negative solution, the charge on the solution, it's going to become large. So up till a certain point, at a certain point, the positive charge on the electrode would become so large that it will start attracting electrons back from Cl ions. So now the reverse reaction would also start. So your second reaction, which was not feasible initially, that is also going to start, and you're going to reach an equilibrium. So there's going to be both forward. Cl2 would gain electrons. This will become positively charged. It will become so positively charged that it will try to gain those electrons back from Cl-1. And so it's going to be a cyclical reversible reaction. Okay? Is this clear, this one?
Yep, it's clear.
So the only difference now is that in the previous case, the substance wanted to lose electrons, so you had more electrons. Now the substance wanted to gain electrons, so your platinum electrode is now positively charged. So all you have to do is just measure the potential. So you attach so you attach a voltmeter, and that voltmeter would measure the potential. That's your standard electrode potential. And that one will have a value of 1.36 volts. Okay, that's already been measured. The positive potential indicates that it likes to gain electrons. Okay, let me So a higher or positive potential. So it indicates that chlorine likes to gain electrons, which we already knew. Now we can kind of make electrodes out of, there's a third type of electrode as well. We can kind of make electrodes from any substance. So do you think, do you think fluorine will have a higher potential than chlorine or a lower potential?
Higher potential.
Okay, so it's going to have a higher potential because it has an even stronger tendency to get. So if you had fluorine over here, there would be the potential on this would be more positive. If you had iodine, iodine does not have that higher potential. So it's not, iodine isn't even a gas. So you're not going to use this electrode. Uh, so you can have a look over here. Fluorine's got the greatest tendency to gain electrons. That's plus 2.87. Iodine, this one is iodine. That's slightly lower. That's 0.54. Bromine would be somewhere in the middle. You got bromine over here. That's 1.07. You've got KMNO4, this one. It's a very good oxidizing agent, so that's got a higher potential because it likes to gain electrons very, very strongly. So KMNO4 is a good oxidizing agent. You got Cr2O7 that also has a pretty high potential. That means it likes to really gain electrons. Okay? So we've got a scale of potentials, different potentials that could be measured. And you can figure out the relative tendency for what the substance likes to do. So we've got 0, you got, I mean, usually it's just +1. And on this side, you got -1. Now remember, this is your E0 scale. Higher means a gain of electrons. That means that indicates that it likes to gain electrons. Meanwhile, lower indicates loss of electrons. It likes to lose electrons. Okay. So is this clear, the scale?
Yep, it's clear.
And also remember that potentials are relative. They don't, I mean, the value itself doesn't really mean anything. I mean, if I say something has 2 volts, right? It means absolutely nothing. It's always a relative comparison. I mean, it's like everything is basically, I mean, the value itself, like anything that is measured, the value itself doesn't really mean anything unless you compare it with something. Like if I say that something, if I say someone is like has a height of 5 feet 6 inches, right? Then it's always relative to something. Like, so how are you measuring it? It's relative to from the ground, right? That's what the height is. When you try to measure tall buildings, uh, if somebody says that it's 80 meters high, right? So you have to mention like compared to what, like compared to sea level or compared to the base of the building or what, right? So everything uh, is comparison. So remember, the values itself don't mean anything. You just have to understand that there's a higher voltage and there's a lower voltage. Okay, if I say someone is taller than, if I say someone is tall and the other one is short, right? The heights could be measured in centimeters, the heights could be measured in inches or yards. I mean, the value itself doesn't really mean anything. It's just a relative comparison. They just help you compare the two things, right? So is this clear? Okay, don't. So basically, what I was trying to say was, don't think of it in terms of negative and positive. Just think of it in terms of higher and lower. Is that clear?
Yeah, that's clear.
Okay, so you're gonna have higher. So it doesn't really matter if all the voltages are positive. If one of them is the higher voltage, the other one is obviously the lower voltage. So one of the higher one is referred to as the positive one. The lower one is referred to as the negative one. So even in batteries, etc., the positive and negative terminals, uh, it's just that the higher one is the positive, even if it's not, the value itself in the data booklet is not positive, it doesn't really matter. The higher one is the positive, the lower one is the negative. Okay. So we're going to continue tomorrow. You clear enough? So that's the whole topic basically. The simple thing is just remember this. Higher potential gains electrons, lower potential loses them. Okay.
Okay.
So let's continue tomorrow then. Okay.
Okay, thank you.
Okay, take care.
I love it.